So, we have been looking at, so in the last class we ended the class by saying that at room temperature in barium titanate, the titanium sort of moves up from the center of the octahedral void position, octahedra defined by the oxygen octahedra, and oxygen octahedron also distorts at room temperature, and that gives a dipole moment in a single unit cell, right. So, now single cell, right. So, I am not going to call it unit cell. So I can call it what is called the single cell that I am going to talk about is what is called a pseudo cubic unit cell. If the material were cubic, this would have been a unit cell, right. So, my unit cell is I have bariums at the corners, I have an octahedron of oxygen, right, and I have titanium at the center, right. So, this is oxygen, this is oxygen, this is oxygen, this is oxygen, this is barium, this is barium, this is barium, this is barium, right. So, this is my unit cell if it were a cubic, right. So, this is my unit cell if my structure were cubic, right. Now, I will, and hence so even if the structure is not going to be cubic, I am just going to call it a pseudo cubic unit cell for all the other structures. Pseudo cubic, it is not a real unit cell, it is a pseudo cubic unit cell. If it were cubic, this would have been the unit cell, but it is not cubic, right. So, this is not a real unit cell, but it is a pseudo unit cell or a pseudo cubic unit cell, okay. So, I am going to call it PCUC, right. So, pseudo cubic unit cell. So, if let us get back to our pseudo cubic unit cell. Our pseudo cubic unit cell has a polarization now has a let me be very precise here. So, it has a dipole moment which is in this fashion, okay. Now, let me look at the second pseudo cubic unit cell which is right next to this, right. Even in the second pseudo cubic unit cell, something like this should happen, right. Now, so in this unit cell, this I will call it as PCUC1 and this is PCUC2, okay. In PCUC1, titanium has decided to move up, right, okay, but so that it can fit into this octahedron, right. So, titanium moves up, whereas in PCUC2 what is so special about moving up, it could have moved down also, right. So, titanium could have as well moved down, right. Now, if this happens randomly, right, let us continue this here. If this sort of moving up and down happens randomly across unit cells, sorry, let us select this color. So, if so in one unit cell it moves up, in a few unit cells it moves up and then it goes down, so and then it goes up again, it goes down again and so on and so forth. If it is just randomly oriented, randomly you are creating random creation of dipole moments in every unit cell, then our net polarization is actually 0, right. So, because I am just adding up. So, what is PR? PR is nothing but sigma Pi divided by in a unit volume, right. So, what is the total polarization in a unit volume? That is my sorry, what is the total dipole moment? This is the dipole moment, and this is dipole moment in a unit volume, right. So, that is PR, right. But if sigma Pi is so randomly it is going up down, sigma Pi itself equal to 0. If dipole moments are random, and PR equal to 0. So, this will not give any ferroelectricity, right, but you will have, or this will not give any spontaneous polarization, right. But where is, but how does spontaneous polarization come from? It arises when this titanium moves up, right, the titanium in this octahedron moves up and it talks to the next titanium and it tells you, look, I am moving up, I want you also to exactly do the same thing, you also should move up, you also should move up. This talks to the next octahedron and say, you have to move up, you have to move up, and so on and so forth. So, there is some sort of long range dipole. So, I am creating a dipole here, dipole interaction. Okay. In one unit cell, yes, okay. So, to satisfy the structure, right. So, to make sure titanium fits in this octahedron, titanium sort of moves up, right. It created one dipole moment, but this dipole moment should talk to the next unit cell and say, look, I am moving up, so you also move up. This guy talks to the next person and says, next unit cell and the next pseudo-cubic unit cell and say, I am moving up, so you also better move up, right. And that creates some sort of a long range order, right. So, long range dipole interaction which creates a long range order, right. Now, if I do my calculation of PR equal to sigma Pi divided by V, I have so this sigma Pi is not going to cancel out because I have long range polarization order, right. So, I have long range dipole order, right. So, but that comes because each dipole is interacting with each other, right, and that is non-zero. So, then I have there is spontaneous polarization. In fact, it is all these ferroelectric materials have this positive coupling, right. So, dipole coupling, this is just pure electrostatics. So, all the ferroelectric materials have a positive or interaction, which is dipole interaction, which means the dipole moment of one unit cell is going to tell the next dipole moment that you should also stand up, right. So, by doing that so by making a configuration of dipoles which is like this, right, given the dipole interaction is actually attractive, right. So, then you are actually reducing the energy of the system. This is the least electrostatic free energy in the system. Okay. So, if systems want to minimize their free energy, so as a result if aligning and then cooperating with each other is good, right. So, that brings some stability or that brings that reduces the energy of my so if I follow a system, right, if so in a country if I follow a system and then that makes my country stable, I would rather fall in line and follow the system, right. So, because for greater good, here the greater good is minimization of electrostatic free energy, and so if I align, if all the dipoles align and then cooperate with each other, right. So, and then follow this system, then that is good for the material itself. The material has a lower electrostatic energy and so this is for infinite material, right. So, if there are finite size effects and other things, we will not do it right now, but so and hence so I have a spontaneous polarization that is stabilized in my material. Okay. So, this is what happens in materials with spontaneous polarization, right. So, all I have I have a dipole moment, but all these dipole moments talk to each other. Okay. So, because they are talking to each other, there is going to be so if this is dipole moment up, this will also be dipole moment up, this will also be dipole moment up, and so on and so forth at an so I am going from an atomic scale of one dipole moment to a larger solid scale of many dipole moments, all of them talking to each other and all of them pointing up, right. So, then I have a spontaneous polarization. Okay. Now, if I have a spontaneous polarization, I said that so now I started so in a paraelectric phase or in the high temperature phase, I said my underlying space group, my underlying point group is M3 bar M, right. Now, this can in the low temperature phase with spontaneous polarization, so it cannot be M3 bar M, the underlying point group cannot be M3 bar M, because M3 bar M is not polar, right. So, rather it goes to what is called a polar point group. So, as you can see, if I am changing temperature, right, so I am going from high temperature phase to low temperature phase, so the symmetry also changes, right. So, it becomes from a higher symmetry, or I mean, so the M3 bar M, which has more symmetry elements, to a lower symmetry polar point group. It will, so in case of barium titanate, that point group is 4 mm, right. So, 4 mm is the polar point group that it goes to. Now, what is 4 mm? 4 mm is a tetragonal system. I started with a cubic system, right. I started with a cube and said, okay, so I have bariums here, I have titanium at the center, I have oxygens here, right. And what I did to this cube, I took took every individual octahedron and I sort of applied some sort of a tensile strain, right. So, as a result, if I take a cube, right, so here A equal to B equal to C and I stretch it along C, right. So, then I am going to come to, I am stretching it along C, then I go to a configuration where A equal to B, but A equal to B less than C, because I am stretching it along C, right. So, then that becomes a tetragonal system. Okay. So, now I have a unique axis, right. So, and then the point group is 4 mm. So, I have a unique fourfold axis about which I am also generating a polarization, right. So, now the the structure is going to look something like this. So, the titanium has moved up, right. So, the oxygen octahedra also have distorted a bit, right, and then I have my barium atoms which are sitting at the corners of the tetrahedron, right, tetragonal unit cell. Okay. So, what I have is now a 4 mm is my point group and 4 mm is a polar point group. And that means that barium titanate has a spontaneous polarization. At low temperatures, right, at room temperature, let us say. Okay. Okay. So, that is how so that is the atomistic picture of how materials get their spontaneous polarization. Now, barium titanate, so also the other part, the electrostatics part is that there is a spontaneous polarization, but the same spontaneous polarization also comes for aluminum nitride, gallium nitride, etc. But you can call barium titanate a ferroelectric because this titanium displacement which has gone up, right. So, when all the titaniums have in coordination gone up, right. So, the dipole moment is this way, the spontaneous polarization is this way. When I apply an electric field, all of them should come down, right. So, this is the ferroelectric switching. So, it is sort of like titanium has coordinatedly gone up, but they should all coordinatedly come down, right. So, that is so it is not as easy as what I just said, but this is what if this sort of switching happens upon the application of electric field, then so that material is ferroelectric, and indeed in case of barium titanate such a switching does happen at fields which are few hundred or so less than 100 kilovolt per centimeter. Barium titanate switches from PR to minus PR, right. So, the spontaneous polarization is PR, polarization is facing up, but it becomes minus PR where polarization faces down. Okay. Now, let us look at some of the visualization of whatever I was just saying. So, let me open VESTA. And let me open for you first in VESTA, sorry, not in VESTA, rather in the folder called structures. I will open a paraelectric barium titanate, and I am going to also open a ferroelectric barium titanate, Okay. So, these are the structures, all right. So, first let us look at the paraelectric barium titanate. So, you can see that these are all, so there is a titanium here, right. So, this blue atom here is a titanium, these are bariums, I do not know. So, can you, yeah. So, you can see the arrow mark, right. So, the arrow marks are barium, the green big atoms are barium, the titanium atom is this blue atom, and the oxygens are all the red atoms, right. Now, you can clearly see that there is an oxygen octahedron here, this blue color thing is an oxygen octahedron, it is a very nice octahedron, right. So, this has the 3 bar 4 symmetry, 4-fold M3 bar M symmetry, right. So, the center of this octahedron has an M3 bar M symmetry. Okay. So, this is the paraelectric phase where all bonds are nice, right. So, I have an oxygen titanium oxygen bonds which are straight, right. So, titanium oxygen titanium bonds which are straight, all these octahedra are nicely perfectly aligned with respect to each other, right, and so on and so forth. Okay. So, this is a cubic barium titanate, right, and in fact I can look at the positions of where titanium is. So, these positions can be determined from X-ray diffraction. Let me go to the structural unit cell. So, unit cell is cubic unit cell. So, P M3 bar M, that is my M3 bar M is my underlying point group, the P thing we are yet to look at, that is the space group. And you see that bariums are at okay. So, here the positions are slightly exchanged, they look at titanium as the origin, barium, if titanium is the origin, barium then becomes the body center. Okay. So, barium is at 0.5 0.5 0.5 and oxygen then becomes so 0.500. So, all 0.500s, which means 0.500, 0.50, 0.5, all those are positions of oxygen. Okay. So, very symmetric structure, very nice and cubic structure. Okay. Alright, so that is the paraelectric phase, right. So, which is the boring phase, very symmetric, right. So, you do not really have the property of ferroelectricity here. If you want to get to the property of ferroelectricity, you should go to a ferroelectric or a polar phase, right, which is less symmetric. You reduce the symmetry, you generate new properties, you see. So, that is the idea from now on, right. So, if you have to do any sort of material engineering, right, if I am going to really high symmetric materials, the amount of properties that I can extract, fancy properties like ferroelectricity, piezoelectricity, etc. If I want them, right. So, if I want my material to be capable of having some ferroelectricity, piezoelectricity, etc., I would like to not go to really this cubic nice structures. I would like to reduce the symmetry, and then reduction of symmetry yields newer tensors, newer tensorial elements, right. So, similarly ferroelectricity. So, if I reduce the symmetry here, so what did I do here? So, here for example, I am viewing barium titanate along C axis, right. If I look at the unit cell again, so the unit cell has now A equal to B, it is P4 mm, 4 mm is the underlying point group. So, I have 3.99, 3.99 A equal to B, whereas C is stretched, right. So, C is 4.04 angstroms, right, whereas A and B are 3.99 angstroms, right. I am seeing this along the C axis, right. So, this structure I am sort of visualizing it along the C axis, I will keep this. But and so I so if I am seeing it along a symmetric axis, I am always seeing this 4-fold axis of rotation, I am seeing a lot of symmetry elements, right. So, let me view it along the A axis, so that I do not so this is along the C axis, I change it to along the A axis. Here I can clearly see, right. So, look what is happening to the blue titanium atoms, right. So, I go from C where titanium looks symmetric, right. So, but because there is 4-fold axis of symmetry, it is a it is something to do with projection. However, I look at it along the A axis, you see titanium is nice and centered. I look at it along the A axis, titanium has moved down, right. So, in this case all titaniums are moving down, all the oxygens are sort of moving up, right. So, or this oxygen and this oxygen have moved up, right. So, so I have made a distorted octahedron of oxygen, and I have made titanium where the polarization has titanium has moved down, right. So, I did this sort of a thing, right. So, with respect to this unit cell. Okay. Now, titanium, we know that titanium has moved down and oxygens so some of the oxygen octahedra has distorted. So, the question is, can we actually find out the remnant polarization of this crystal, right. So, of this structure, right. So, and titanium has moved, just to see where titanium has moved, you can see that from structural parameters. So barium, okay, so here again we are back to barium being my origin, this is what I defined. So barium is the origin 0 0 0. Titanium is 0.5, but along the z axis it is not 0.5, it is supposed to be at 0.5, but it is at 0.476. 0.476 times the c axis, right. So this is some so these are what are called positions in a unit cell. So you are normalizing it with respect to the length of the unit cell, right. So this is 0.7 times c, right. So titanium is not exactly at so if I start barium is 0 0 0, titanium is not at 0.5, it is at 0.5, that is okay, but along the c axis it has moved down a bit, that is this moving down, right. So that I have shown it is not at 0.5, it is at 0.47 or 0.476. Okay. The oxygens on the other hand, right. So oxygens also have some sort of a displacement, they are not exactly at 0.50, right. So the oxygens which are let us go back. So let me start with barium 0 0 0, right, and this barium is at, this is 1 0 0. Okay. So this barium again is at 0 0 1. Okay. And then this barium is at 1 0 1, right, and so on and so forth. So this is the projection I am looking at, but you have the other side also. Okay. And so I have titanium which is supposed to be at 0.5, but it has moved down to 0.5, 0.476. Okay. So titanium has moved down. What about oxygens? So oxygens, so I have one oxygen here, it is supposed to be exactly on this plane. So the position of this oxygen, right, if I make it red is supposed to be the symmetric position of this oxygen before distortion. So that was supposed to be at 0.50, right, but that oxygen now has converted or has changed to oxygen which is 0.5, and this oxygen has moved a bit up, right. So it has moved up by we can check VESTA 0.043, I think 0.043, right. So that is the oxygen position. So I go back and write that this has moved up by 0.043. Okay. So if this moved up by 0.043, this also would have moved up by 0.043, right. So that oxygen 1, right, oxygen 2 is 0.5, 1.043. So it is 0.5, now it has moved to 0.5, 1.43. Okay. Then what about oxygens 3, 4, 5 and 6, right. So those are oxygens in this plane, right. So they all so since I have to preserve fourfold axis of symmetry along this direction, they all should move up simultaneously, right. So they all should move up to the same extent, right. So oxygen 3, oxygen 4, oxygen 5, oxygen 6, right. So what are their positions if we calculate properly? So they have moved up from 0.5 to 0.53. So ideally it should be at 0.5 sorry, yeah, 0.5, 0.53. So 0.5, 0.53, right, or 0.5, 0.50, 0.53, that is the second oxygen. So O3, this is O4, then I have O5 which is 1.5, 0.53, right. So that is just one lattice separation, right. So for this oxygen, if this is 0.5, 0.53, this will be 1.5, 0.53, right. And then I have this is O5 and O6 is 0.5, 1.53. Okay. All right. So these are my oxygen positions. Now the new oxygen positions O1, O2, right. So the new titanium position is 0.5, 0.5, 0.476, and the new barium positions, barium is still symmetric, are 0, 0, 1, 1, 0, 1, 0, 0, 0, 1 0 0, then I have 0 1 0, then I have 1 1 0, 1 2 3 4 5 6, I have a 1 1 1, and I am missing one more position, right. So, yeah, I think 0 1 1. Okay. So, these are all the barium positions, right. So, I have barium positions, I have titanium positions, and then I have oxygen positions, right. These are all the oxygen positions. All right. So, then I can do the calculation. So, what is the Pi, right. So, polarization in the unit cell I is just sigma Qi Ri, right. So, I can do this in this brute force way, or I can also see that the only displacement that is happening, right, is along the z axis, right. So, in the z axis oxygen is getting displaced, 4 oxygens are getting displaced slightly differently compared to the other 2 oxygens, right. And so for example, if I take if I just look at the displacement of oxygen 1 and 2, right. So, from this so oxygen 1 and oxygen 2, right. So, both of them have, so oxygen 1 and oxygen 2, both of them are displacing only along the c axis, right. So, if I look at this, so if I just take the oxygen displacement here and then go to the next page, O1 and O2, right. So I am just going to look at the c axis coordinate, right. So, the calculation then becomes 1.043 plus 0.043, right, times the charge on these two is actually 2 by 6, right, plus O3, O4, O5, O6, all of them displaced together, right. So, that is this is oxygen. For oxygen, what is sigma Qi Ri, right. Q is minus 2. Okay. So, plus if I look at the other oxygen, how much did it displace? Structure parameters. So, the other oxygen has displaced to all the plane of oxygens, the 4 oxygens have all displaced by 0.533, right. So, they are at 0.533 now. So, times 0.533 times minus 4 by 6, right. So, this is the oxygen charge, this is the center of mass of the oxygen charge. Where is the center of the oxygen charge? Okay. Now, where is the center of mass of, this is the center of mass of anion charge, anions. Okay. Center of mass of cations is 4 times titanium position, and titanium is at just the c axis. I am just going to consider the c axis, right. So, titanium will be at what is the position of titanium? 0.476, right, plus 2 times the barium position, and barium you can see that all bariums are symmetrically arranged, correct. So, the center of mass of all these, if I can multiply 2 times 001 plus 2 times 101 plus other things, but that will just come out to be so barium, I just have 2 is the charge on barium times it will be 0.5, right. So, the center of mass of barium will be just 0.5. Okay. So, now what is the total Pi, right. So, total Pi is 4 times 0.476 plus 2 times 0.5 minus 0.5 this number, right. So, 1.043 plus 0.043, that is actually so times minus times 1/3 minus 0.533 times 2/3. Okay. All right. So, yes. So this is going to be your so this is the total Pi, but this is in atomic coordinates, right. So I have to so and then I have to multiply it with the charge, right. So with E, because here I am just taking charge as 2 positive charges. By charge meaning 2, I mean it is 2E, right. By charge meaning 4, I mean it is 4E. By charge meaning minus 2, I mean it is minus 2E, where E is that 1.609 times 1.6 times 10 power minus 19 coulombs, right. So, that is the charge of an electron, right. This is the total Pi per unit cell. Okay. Now, if I want to calculate the PR is nothing but sigma Pi divided by V, right. But so that is nothing but the P of a unit cell, because all the other unit cells exactly will have the same charge, divided by volume of the unit cell, right. And also, okay, so the positions are just the C positions, right. So, I have to also multiply this with the C lattice parameter, right. So, E times C, okay. So, if I actually solve this properly, PR equal to E times C divided by A times A square times C, where A is the lattice this is A and this is C, right. So, that is the volume, okay. E times C times so this number that we have just written, right. So, if I solve it properly, so I urge you to do that, right. So, you will end up with a PR, which I solved it yesterday before coming to this class. So, it will be about 0.31 coulomb per meter square, right. So, just by looking at the structure and displacement of titanium and assuming titanium has 4 plus charge and barium has 2 plus charge and other things, so the spontaneous polarization can be calculated to be 0.31 coulomb per centimeter square, and this is lot of charge, right. So, this is one of the higher sides, right. So, typically people express this in terms of micro coulomb per centimeter square, or coulomb per meter square is also okay. So, you have about 30 or 31 microcoulomb per centimeter square, that is the spontaneous polarization that exists in barium titanate. So, if I am switching it, I am switching from plus 31 to minus 31 microcoulomb per centimeter square. So, then I can think of making devices where plus 31 microcoulomb per centimeter square is a bit 1, minus 31 microcoulomb per centimeter square is a bit 0. So, I can make a memory out of such materials, right, such ferroelectric materials. Okay, but we just looked at the structure, we looked at the symmetry, we looked at the positions of atoms, right, and then we calculated the polarization. This is a simple calculation, right. We used aspects of symmetry to say that okay, there is a 4-fold axis of symmetry. So, all the oxygen should have moved, so all the oxygens which are in a plane perpendicular to the 4-fold axis should have moved simultaneously, right. So, and then we have used ideas of symmetry also to say that so okay, so so there is a 4-fold axis, right. So, if I stretch it, there is a polar axis that comes up, right. So, we have used the ideas of and we said that we will only look at displacement along the C axis to simplify my calculation, right. So, you can look at the symmetry and then get these sort of estimations, right. So, symmetry of the crystal and get estimations of so in this case we have calculated the spontaneous polarization in barium titanate, okay. So, in assignments probably I will let us see how to do that, but I will try to give you problems where you can actually calculate the spontaneous polarization of slightly other sort of crystals such as aluminum nitride, just by looking visualizing the crystal structure and then estimating this sigma Pi sigma Qi Ri, that sort of a calculation, okay. So, with that I think for now we will halt the discussion on ferroelectricity, and in the next class we will move towards looking at space groups and come back to a certain crystals and look at the how to read space groups, how to understand space groups in a crystal and things like that. We will come back to some more functional more popular crystal structures such as a woodside, such as a diamond cubic structure and so on and so forth, right. So, silicon has what is called a diamond cubic structure, and silicon is very good electronic material, right. So, silicon is so if I talk about an electronic material, the first material that comes to your mind is silicon, right. So, what is the structure of silicon, what is the space group, how can I understand the symmetry elements in silicon, right. So, we will look at that, we will look at diamond cubic, but then so we have already looked at some basic units such as the tetrahedra, etc. So, how do we align this tetrahedra to get to various different crystals, right. So, this sort of a formalism we will do in the next class and probably stop the discussion on symmetry there. Okay. So, with that I will see you in the next class.